Okay, thank you. So what I pretty much wanted to do today is to answer any questions you might have, and if you don't have any questions, maybe we can just try to solve together one of the logic programming problems, which would be similar to the one that might be on the final exam. And also, maybe you can share a little bit if you had any experience with examus, with proctoring exam. Maybe you can tell me, because that would be my first experience, and I honestly do not exactly know how it works and what to expect. Did you have any experience with examus before?
Yes, we had experience. It sometimes fails uh, because we can lose our connection. I
Mm-hmm.
don't know exactly how it works now. Probably it works now better
How
than
does it
was.
work in principle? Is it like you do screen sharing and you solve like whatever you do, the proctor can see, or is it like a webcam and the proctor can see everything around you?
Yes, we turn on our camera and share our screen.
Mm-hmm. So in principle, I can say that everyone shares the screen and does the exercise like in real time, and I can check periodically like who does what, right?
Yes.
It would work like that. Cool. So what we would do, like the final exam, we have it on 28th, or I don't quite remember the exact date. Do you know by any chance?
No,
I
I
think
don't
it's
know.
28th. So yeah, it would be probably like 1 hour and a half. You would have a few multiple choice questions, and then a couple of problems to solve. Probably one logic programming, one functional programming. And that would be, I think we agreed 40% of the final mark, and then 30% for labs and 30% for midterm and intermediate tests, right? That was, I think, the breakdown that I announced in the beginning. So let me share the screen as well. So you have seen, I hope everyone has seen this table with current grades. So you have the midterm exam here. You have labs for labs, and you have 2 intermediate tests, which is like lists and deeply functional thing. There are 2 columns. One of them is number of points, and the other one is number of points. It's like the mark from 1 to 10. So that would be averaged out to produce the final result. And you can see your current progress here. So if you do not see your grade here, you've done the lab, but the number is not here, let me know. I typically go through the table in Teams, which has all the links, and check them and put the mark here. And you should have received like specific comments on your code. Yesterday, when I was like checking all the labs, I was leaving comments as issues in GitHub. Any questions that you have, like, to me on the course, like on the final exam? Okay, so I think what we can do, we can try to do one of the reasonably like moderately complex problem in Prolog and see how it works out.
Sorry, could you explain, please, how to convert from tail recursion to co-recursion, for example, for factorial or something else.
Okay, let's do that. So we have first of all, we have two types, recursion and co-recursion. And normal recursion can be tail recursion or non-tail recursion. So let's start with the very simplest one. The simplest one for factorial would be like normal recursion. So we would say that factorial of 1 is 1, and factorial of any number n is f, if. And then what we need to do, we need to subtract 1 from n. So we say n1 is n minus 1, factorial n1 f1. And then final result f is f1 times n, right? So that is the this is the normal factorial, and we can check it. Factorial 5 is equal to 120. And now if I press semicolon to try to search for other solutions, I would have problems. So I will not do that. I would have problems because the first rule in fact matches number 1, and then second rule also matches number 1, which calculates factorial 0, factorial minus 1, and so on. So we have this infinite tree. And to get rid of this, I would need to say here n is greater than 0. Or what I could also do, we have not learned that in details, but there is a special predicate called cut, which is denoted by exclamation mark. And what cut does, it kind of prevents prolog from matching other rules. So like when cut executes here, it would not match any other rules for factorial in the same kind of invocation. So when I invoked factorial 1, when I asked for factorial 1, when cut fired, no other rules for factorial 1 would be executed, and no other backtracking would not go beyond this cut predicate. So if I load this program, you see it gives me just one solution. It even doesn't ask me for semicolon, so it knows that there are no other solutions. So that would be normal recursion, right? So if I want to convert it to tail recursion, what do? I need to introduce accumulator. So I would say, let me start from scratch. So I would say my main rule, let me start with the main rule. My main rule would be like that. I would have factorial of n. I would have some accumulator a, and the result r. So what would I do? I would calculate n1 is n minus 1. Then I would need to multiply before the call, right? So I would multiply accumulator by n. I would say a1 is n times accumulator, and then I do the call. I say factorial n1 a1 r, and r is reserved for the result, right? So I do not, when I go deeper into recursion, I do not change this variable. It's just passed as a reference throughout this recursive dive. And the final rule would be 1. When I reach 1, I would say, okay, I will return the accumulator, right? And then finally, I would need to provide the rule as an interface, like so that I call the factorial with n and f, and this would call factorial n1f. So that's it, and I say factorial 5 x equals 220. If I ask for other rules, it also goes into infinite loop for exactly the same reason. So I would have to put cut here as well. Any questions here? So let me maybe draw the tree, how this is executed.
No, I think it's clear now.
It's
Thanks.
clear. So no need to draw the tree. Okay. Then the co-recursion. This is actually goes into infinite loop and it does not overflow. In the previous case, if I try to calculate another solution for factorial 5, it would give me stack overflow. This one doesn't give stack overflow, it just goes into infinite loop, which is kind of better. So for co-recursion, I need to think differently. Like for co-recursion, I want new solution to be provided upon each new call. So I want first solution to be returned is 1. So I would say factorial 1, 1. That would be the same. And then if I ask for more solutions, I would want another solution to be obtained, right? So I would say factorial nf. So how would I go about that? In co-recursion, remember in F#, what we did, we return the first element of the sequence if we do co-recursive definition. And then we try to produce new elements from like existing elements which we obtain in a co-recursive call. So we like say, we would first yield 1 and then we would take sequence of factorials obtained using the same definition and then do something to it and produce new sequence of factorials. So it's kind of the same here. We return first solution factorial 1, 1, and then we rely, we kind of return other solutions. So we say factorial n1 f1, and then we see like what do I have to do to produce next sequence of factorials from this. So if I, for example, have the fact that factorial 1 is 1, how do I produce next factorial? I say n is n plus 1, and f is f1 times n, right? Let's see how this works. Factorial 5x. Oops.
N
Yeah,
is
this is
N1.
n is n1 plus 1, like this. Yeah. Okay, thank you. So 520, and then it goes into infinite loop again because it is co-recursion. Why doesn't it stop? So how is this executed? It is executed very differently from normal recursion. So let me have this here. So when I say factorial 5x, what happens is that the second rule is matched, and let's not make it 5. 5 is horribly big. Let's say it's factorial 3x. So the first rule is matched. It goes into factorial. Well, actually, let me start a little bit differently. So let me load this. Oops, this still does not want to stop. Okay, so let me put it this way: factorial xr, and it would give me 1, 1, then 2, 1, 2, 2, 2, 3, 6, 4, 24, 520, and so on. So it would produce this infinite sequence of factorials, right? So how it would produce the infinite sequence of factorials? I say factorial xr, it would first match the rule factorial 1, 1 and give me x equals 1, r equals 1. If I want the new definition, it would go into second definition. It would say factorial n1 f1, n is n1 plus 1, f is n times f1. So, and this would lead into the fact that it needs to calculate factorial n1 f1. It will, the first solution would give me n1 equals 1, f1 equals 1, and this would give me n equals 2, f equals 2. And again, the same thing here, but it would be n1 prime and some other variable for n1 prime, f1 prime. And this solution would give me n1 prime equals 1, f1 prime equals 1, n1 equals 2, f1 equals 2, n equals 3, f equals 6. Okay, and so on. So on the left branch of the tree will return me a new factorial each time. So that's the co-recursive definition. If I ask this co-recursive definition for factorial of 5, the way it would work, it kind of ignores this 5. So what happens is, like if I say factorial, I can calculate the factorial in this way. I can say factorial xn, and x equals 5, right? So how this thing works? Factorial xn generates factorials, right? So it generates factorial 1, 1, and then it checks if x is equal to 5. It says no, it doesn't. It's not equal to 5. Then it goes back and it produces next factorial. So it does this kind of forward and backward backtracking until this x equals 5 is not satisfied. When it is satisfied, okay, it's the result is returned. Again, if I want this not to go into infinite loop, I think I need to put cut here, and this would give me, sorry, it would not work this way, because if I put cut here, factorial would not work correctly. It would just return me one result. So I need to be more clever than this. I need to say factorial xn, x equals 5, and then I need to do cut. And this would give me, I need to reload the definition. And this would give me just one result. So to be absolutely good with this, I need to say this like co-recursive factorial, and then I can say fact xr. I do c fact like say y r, and then x equals, no, actually I think I can do c fact xr and then cut. Yeah, that would be sufficient. Gives me, it will not generate factorials, but it would produce it should produce the result. Why it's not working? So this gives me the result, but this would go into infinite loop. This does not give me the result.
Probably we should use cfact in second line. Cfact.
Ah, thanks so much. Yeah, that's correct. Thank you. Yeah, this gives me now one result. Cool. So, any other questions on co-recursion? Okay. So one example I wanted to consider today is like binary tree sorting. Like if I want to implement a search tree in Prolog, how would I do that? Because we have not spoken explicitly about trees, about data structures, but the important thing to know is that in Prolog we do not have types, but we have structural terms. So we can, for example, say that we would represent a tree by some kind of term. Let's say the node of a tree would be denoted by n, and then the value, and then left and right subtree. And we can agree that like certain atom would be used for empty tree, right? So, for example, if I want to implement the search tree, I would need to implement insert operation, right? So I would say insert, and then if I want to insert something in the empty tree, I would agree that nil stands for the empty tree. So if I want to insert number x into an empty tree, I would return node of x nil nil, right? Then if I insert, let me put the element first and then the tree. So if I want to insert x into the node x AB, I would return x AB, the same tree, because I do not care about duplicates. Like I would consider like the binary tree to have no duplicates. Then if I insert x and y AB and y, let's consider the case when x is smaller than y. If it's smaller than y, then I need to insert into left subtree. So the left subtree would be modified. It would be a1. So in this case, x is less than y, and I go and insert x into a and produce a1, right? And the same for the right subtree. B1, B1, right? So that should more or less work, hopefully. I will not test it because I'm lazy. I mean, let's implement the second part. Like, how do I insert all elements of a list into this subtree? Like, let me call it tree to list, the predicate. Actually, list to tree. So I have the first argument is the list. The second argument is tree. So for empty list, I return for empty tree. For non-empty list, what do I do? If I do non-tailed recursion, I produce the list to tree from the tail. From the tail, I do R1, and then I insert X into R1, right? So something like this. And produce R as a result. Good. So let me do list to tree, any sequence of numbers, and R. So that's what it gives me as the result: 8, 6, 2, 3. Is it correct? Let's yeah, so it's kind of inverted 3, but it looks more or less right. Okay, how do I then convert it back into list? How do I traverse a tree? So let's say tree to list. I have tree as the first argument and list as the second argument, right? So I do it like this, and then if I have non-empty tree, node x a b, what do I need to do? I need to convert left subtree into list. So I say tree to list a ar, tree to list b br, and then I need to return the result. What would be the result? Result would be the list L, and I need to concatenate AR, BR, and the element X. How do I do that? Anyone? Can you advise me, please? Like this, probably. Then if I want to sort, I would do list to tree L there, tree to list there R. Let's see if that works. Beautiful. So this is the tree sort, which you can do in Prolog. Any questions? How do we make this tree to list tail recursive? Are you still with me, by the way? Yeah, looks like so.
Yes.
How do we make this tree to list tail recursive? Because that's the easy thing to do. So we need to add accumulator, right? So let's start with the second one. So I have some kind of accumulator here. So I start, let accumulator be this one. A is the bad word. How do I call the accumulator? Z. So so each of those calls should add the elements to accumulator and not return the result, right? So I should have accumulator. So it should work like I pass it a tree and it produces me from one element L1 to the other list L2. It adds elements to those lists. So tree to list A, it adds me from L1. Let me actually call it L and R. That would be more clear. So it starts with L and produces L1, and then the other tree starts from L1 and produces L2, and then to the list L2, I should add R equals X. Well, this is not exactly correct because I should add X before, right? So I should add X to this list L1, X tail L1, and this would be R. Something like this, right? And the final, if I have the empty tree, I do not need to add anything. I just leave the list unchanged. And then the final tree to list, where I have tree and result, I would say tree to list, tree, empty list, and result. Like this, okay? This is tail recursive version. Yeah, it just goes the other way around, but that's easy to fix. So something like this, be ready to do something like this. What else? Make sure that you understand how expressions are handled. I think I discussed that last time, that we have the special predicate called, maybe I have not. So if I have the arithmetic expression, and suppose I want to print it like in some kind of postfix notation or something like this. How would I do that? So whenever I have an expression in Prolog, like if I have 1 plus 2 times 3, it is when I say x equals 1 plus 2 times 3, it does not calculate the expression. It just assigns this expression into this variable. That does not even assign it, just leaves it in the form of the structural terms. So if I say x equals 1 plus 2 times 3 and then display x, it would show me how this is represented inside. Like it's in fact it's the term plus and then 1 and then times 2 and 3. If I say x equals 1 plus 2 times 3 times 4, it would be like this, right? So all those terms, times and plus and minus, they are binary structural terms with 2 arguments. So if you want to do something with an expression, you would need to let me define the predicate P. So suppose I want to print the expression. I would say P, and then I would need to consider different cases. So if I have plus AB, I would call it PA. P. If I want to print in the postfix form, I first print sub-expressions, and then I print plus. Right? The same goes for other operations. Like if I have times AB, I print PA, PB, and times. And then if I have the simple expression like X, I just say I write X. So let's say P 1 plus 2 times 3 times 4. This is 1 to 3 times 4 times plus, which is correct, right? The problem here is that if I ask for other solutions, I would get some other solutions which are not correct. Why does that happen? Who can tell me? Are you still with me, by the way? Understand and following. So why do we have this solution 1 plus 2 times 3 times 4?
Maybe to look to recombinate our functions.
I'm not sure I got that. So the problem here is that it matches when I first ask for the solution, it matches the first rule of with plus. But then if I ask for more solutions, it always can match the second rule as well. So P of X always, like if I say, for example, P of whatever, of any rubbish, it would print me that because I have this P of X, right X. If I, and the second solution would just, for example, take the original expression and print it unchanged, which is something I don't want to have. So what I can do here, I can say here atomic X. So that would check that X here is atomic and expressions would not match. In this case, this would still work. But if I say this, it would give me the first solution and no more solutions because none of the sub-expressions is atomic. Or another way I can do that, I can use cut. I can say here, if I matched plus, I cut and I do not consider any other alternatives. It would also give me just one solution. One more thing I can simplify here, I can use the special operator. There is an operator which converts between terms and lists. So if I have, for example, P ABC, and I say equals two dots L, it would produce me a list of the predicate of the structural term name P and arguments. And vice versa. If I say X equals two dots ABC, it would give me A of BC. So if I say, for example, 1 plus 2 times 3 times 4 equals 2 dots X, it would give me plus of 1 and 2 times 3 times 4. So it only it converts the first level. It does not go into deeper into recursion. So this 1 plus 2 times 3 times 4. So if I show you how it looks, it display times 3 times 4. It is plus with two arguments. First argument is 1, second argument is this one. So that's what you see here, the plus, first argument and the second argument. So using this notation, you can simplify this. So you can say any expression E. If I can convert this E into any operator and then two sub-operators A and B, I print A, I print B, and then I print the operation, right? In this case, I can like solve this with one line for all possible expressions. So I can put here divide and minus, and that would all work out. Okay. Any more questions that you might have? Okay, so those kind of questions you can expect during the final exam. So there would be probably no very complex questions like solving logical problems, because solving logical problems is more creative process. I want to test that you know the paradigm, you know how to write technically, how to write things. So something to do with expressions, something to do with trees, something to do with lists. And finally, the one final example that I want to show you is is how you can solve Einstein's puzzle in Prolog. So you know probably Einstein's puzzle. It's called. It's a pretty straightforward puzzle, which says you have 5 people of different nationalities who live in the 5 houses on one of the streets, and they have different professions. They have favorite drinks and animals, which are all distinct. And houses where they live, they have different colors. And then we have some facts, like Englishman lives in the red house, Spaniard has a dog, Japanese is a painter, Italian drinks tea, and we have this number of facts. And then we need to figure out who lives where and like to find out the whole all data about this street and people who live there. And I don't know actually why it's called Einstein's puzzle. Is it because it's difficult for a normal person to solve in his head, or is it because Einstein was the one who proposed it? But the general idea here is that it's difficult to solve because you need to do search in your head, right? Because only one combination of those houses and drinks and animals would match. But you need to take into account all those constraints. And that's why it's difficult to solve it in your head. You need to do the search in the search space. You need to like consider all possible combinations and then test which one satisfies those conditions. And that's why exactly Prolog is a very good tool to solve this problem, because Prolog supports backtracking. It supports intrinsically, like it supports search. So how can we solve that? Well, there are different possible ways to solve that, and we'll show the most beautiful one and most declarative one. So let's say we represent the street as 5 houses, and each house would be represented by H. H is a structural term. It's just the placeholder by H, and then 5 arguments: the nationality, profession, color of the house, drink, animal, and drink, right? So we know that Norwegian lives in the leftmost house. So that's why when we define this variable street, we immediately say that the left house has this pattern. It's H of Norwegian, and then we don't know what. And this underscore stands for anonymous variable, right? Then we know that in the house in the middle, they drink milk. So that's why we say house in the middle has milk in it. And then what was said about blue house? So this is about Norwegian. So Norwegian lives next to the blue house. So I kind of cheated a little bit and I said that blue house is next to Norwegian, which is kind of, I made this assumption myself and I did not leave Prolog to solve it, but that's a little cheating. So then what do I know? I know that Englishman has a dog, for example. What does it mean? It means that there is a house here which has this pattern, H of Englishman with the red house, right? Englishman lives in the red house. So I would specify it like, what does it mean that in this list there is a house of this pattern? I say member, so this pattern H of English and red should be in this list S. And I think there is a typo here, by the way. This should be also S equals. Okay. And then I say, okay, Spanish has a dog, and it's the same member of Spanish dog, member of H Japanese painter in this list S, and so on and so on. And then it says the White House is next to Green House, and this can be defined in this manner. And the predicate next I can define using append. I mean, it's the fact that 2 elements in the list are adjacent to each other. So White House is greenhouse is next to the White House. Then again, a few facts, and then the fox is in the house adjacent to the house of doctor. Adjacent means either to the left or to the right. And this can be handled here by the definition called neighbor. So fox and doctor are in the neighboring house, and horse and diplomat are also in the neighboring house. And then somebody keeps zebra and somebody drinks water. It's in the question. So how is this executed? I mean, it looks very declarative, right? So I took the problem, and I first of all I decided that I will represent the houses by the list of those structured terms, and then I just say like member. I pretty much take the formulation of the problem and put it here in declarative terms, and it gives me the solution. Surprisingly, I can try it, by the way, to see if it indeed gives me the solution. Yeah, I need to define next, and I need to define neighbor. How do I define the fact that two elements in the list are next to each other? What's the easiest way to do it?
Maybe A, then a vertical, then B, then something else.
So I can say AB if AB are first elements in the list, right?
Yes.
And then I can say next AB something with a tail of T if next AB T, right? I can say that, and that would give me the solution of the Einstein's puzzle. But I can also define next in the slightly different way. I can do it using append, because I can say, okay, A and B are adjacent if I can split the list L, right? Append does also list splitting, remember that. So I can say, okay, split the list L in such a way that I don't care what's the first element, but the second list would start with A and B, right? This can be another definition for next. Yeah, is that clear? So I say, so append is a very clever predicate. So I can use it to concatenate to lists. So if I say append 1, 2, 3, 4 x, it gives me 1, 2, 3, 4. But I can use it in the other way around. I can say append AB 1, 2, 3, 4. And what it will do, it will split it. Like it would give me first solution empty A, second solution A1, B2, 3, 4, and so on. Like it will do all possible splits. So if I write it in this manner, like you can think of it as append does all possible splits, but it only looks for the split where the second list starts with A and B. So if it finds this match, it returns correct A and B, right? Make sure you understand that. This is beautiful, by the way. And you can do like a lot of things with append. You can get the last element of the list with append. For example, if I want to get the last element, I say append, I don't care what, and then the second list would be a list of one element, and that would be 1, 2, 3, 4. That would give me 4. And I can get the element before the last one if I do like this. Right? So it gives me 3. If I want to get the first element, I can also use append, but I should never use append to get the first element from the list, because not in this way. I mean, I should put it in brackets. So this of course works, but to get the first element of the list, I can just say x equals to 1, 2, 3, 4, and this list can be x with any tail. So that is the proper way to get the first element from the list. Because append is a function, it's a predicate which if I ask for more solutions, it would match the second rule, and it would take more time than just do pattern matching here. Okay, so this instance puzzle, the beauty of it is that it is very declarative. I see the pure beauty of Prolog, where I write declarative solution, and it automatically figures out the right matching. Of course, I can also do it like in other ways. There are a few possible ways. I can do it using generate and test, and I can try to represent data in a different way. So let's say I can say Englishman and then the number of house. So, but this is the most beautiful solution and the most efficient as well. So the way it works, I mean, how this solution works. So first of all, of course, S becomes this list, and this list has some uninstantiated variables, right? So it knows that there is the structure called H Norwegian something, but it has those placeholders unfilled. And then when I say member English red, what happens? Member tries to put this pattern of H English red into all possible places in the list. It cannot put it in the first element because like it will not match, right? It will not unify. It cannot put it in the second element because it will not unify with blue. Blue and red are conflicting. But it can match it with the third element because in the third element there is H of something, 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 something milk. And here the first element is H English and red. So it would put when it does the first attempt, it would put English man and red house here, right? Then Spanish has the dog. Where would it put it? It would put it here, right? Because Spanish and the dog. Then Japanese is painter. So Japanese is painter probably would go here. And then Italian drinks tea goes here. Then it says member of H green coffee. So green houses coffee would match this one. And then it says the White House is next to green, right? And this is probably when it fails because it says White House is next to green, and here the greenhouse is the first one, right? So it will not be able to match this rule. So it would go back and it would reconsider green coffee. So it would say that, okay, I cannot put green coffee here. Where I can put green coffee? Not here, not here. I can put green coffee here. Actually, green here, green coffee, right? Japanese painter, and so on. I mean, and then when it checks if the White House is next to green, the green coffee is here, it would deduce that it would also fail because here the house is red and the next house is green, and so this next rule does not match, and it will go back and it will try the next solution. Okay. So that's how it works with the Einstein's puzzle, and finally it manages to find the only correct combination here. So that is something similar to what some of you did in your lab number 4. Okay, so that's I think that's everything I wanted to talk to you about today. And if you have any questions, please feel free to ask. If not, can you please stop the recording? Because if you don't stop and somebody stays in the chat in this call, then it would produce the a few hours long recording, which is not nice. So please stop the recording, and any final questions?